मैम आवाज ही नहीं आ रही।
Hello, Amit?
Yes, ma'am.
Ma'am, shall I introduce and we start?
I think you already done yesterday. I think we can continue, I guess.
Okay, we have with us Dr. Nilima Satyam ma'am for the first session today. She has already taken a session yesterday and she'll be continuing with the topic related to that. So we welcome you ma'am on behalf of IPS Academy Institute of Engineering and Science, Indore, for this 1 week online faculty development program on new approaches in geotechnical earthquake engineering. I request you ma'am to please take over the session ma'am.
Yeah. Thank you so much. And so if you want, we can wait for a couple of minutes if you wish, because there are only 9 participants, not even double digit.
Yes, ma'am. We will wait for 5 minutes.
So your campus is completely open, like offline teaching?
Ma'am,
Yes.
some students are coming. We don't have 100% strength, but yes, it is more than 50%.
Hmm.
Ma'am, what about your campus, ma'am?
We have only PG, PhD students, and not too, like, based on their work. So most of them are here, but the UG students only some of them are there, not complete. So till this semester end, we did the online only, complete teaching.
Ma'am, at present, right now, we are taking offline classes only because of the previous notice of government and RGP.
But we didn't start this offline mode, but online taki next semester we don't know.
Yes.
For a hybrid mode, at least for labs, we should have. So that's a discussion, but because of this third wave or whatever it is, so we could not do anything.
Yes, ma'am. We
So
don't know anything of tomorrow, ma'am. Actually, this is the problem.
no, and ours is a residential campus, right? All faculty, most of them stay, so that's the reason. Okay, so I'll start then. I'll just share my screen.
Yes.
So, good morning, everyone. I hope you see my screen here. And in continuation to yesterday's topic, I thought like I will take up a problem. Soil texture interaction analysis of a pile raft, which is supported for the asymmetrical building. So this is actually part of my first PhD student who submitted sometime in 2016. So she worked on this particular problem, wherein like this is one of the very new thing, because asymmetrical structures have been so common these days. Some structures, even architectures, demand whatever it is without by compromising the stability. So we are seeing all these fancy asymmetrical structures that are coming, and not only the shape asymmetry, even the load asymmetry is something very very commonly seen. So how do these structures behave, especially under seismic environment, and that too when they are sitting on the soft soils where you have like site amplification and the liquefaction issues. So I'll give you the brief introduction with the literature review, why the problem is like novel to handle, and what we have done, like we developed a numerical implementation, or we developed our own code, wherein like two-dimensional SSI analysis can be carried out in a direct approach, wherein like completely the substructure, soil part, substrata, and the superstructure has been modeled as a unit, and then responses in terms of stresses and displacements have been evaluated at different nodes. So anything you do it, especially the numerical thing, it needs to have a validation. So we validated our code with the existing literature, wherein like people have done scale down models like shake table test, and also using commercial softwares like flat. So we have taken their data and try to put it in our model and understand that whether our model is converging to the established or like published literature or not. The next one is like we have done a parametric study like in which wherein like what are the different parameters which will control the overall response of the superstructure, etc. So these are the some of the things which I will be discussing in today's talk. So coming to the first one, like what is DSSI analysis? We have discussed this little bit yesterday. So, but there are significant factors which influence the overall response, including impedance contrast, because soil is not homogeneous, and resonance, damping in soil, as I already discussed in yesterday's lecture. Damping in lateral direction is not same as damping in vertical direction. So we do consider generally 20%. So whereas superstructures or like concrete, whatever it is, that we do consider as a 5%. And then this stratification makes the thing complicated, because that when a wave is passing through particular layer, so there is a lot of wave interactions, and because of the wave propagation in this granular media, so there is a changes in the wave properties as well. So as we say that method of analysis, the commonly used method of analysis, so direct or substructure approach, we have adopted direct approach. And then significance is like you can model the system to the nearest reality, so that so why there are many times this kind of generic questions comes, especially we do get some questions from even the parliament, like can't we build earthquake resistant built environment? So or like these media people, they do ask this such kind of questions, why structures are not able to withstand. So these are the common man kind of questions, right? So it is because we are designing with some parameters of input ground motion characteristics, considering some scenario, but in reality whether that is really happening or not, because earthquake is highly unpredictable and highly uncertain. So we really don't know what is actually the ground motion that may come and hit the structure. Even if it is 0.1 magnitude change, there's a huge amount of difference in the energy, and which may make your structure collapse, or even the duration also, as we have seen in yesterday's Hansen Expressway damage issue. So that's why if you can carry out this SSI analysis, so you can we understand the overall response of the complete system. I'm calling it as a system because there are different things, right? Substructure, that is my soil, and you have a substrata, that is my soil, substructure, foundation, and superstructure. So we do have different elements which are embedded, and which are behaving as a unit, right? So that's why I call it as a foundation system, or like complete system. So then it yields more accurate response to the soil and the superstructure especially, and so that we can have a better build safety and serviceability. So to see some of the asymmetrical structures, and to understand their failure pattern and also the damage intensity. So this is a 1985 Mexican earthquake, where it had a magnitude of almost like 8.1, and as you can see here from this particular image, so this is a L-shaped building, and this is also actually the same building but in the front view. So the top floors, they failed because of the inertial effect, and mostly during this earthquake, this is the same earthquake wherein like Hansen Expressway also, this is classical example, classical earthquake I can say, wherein the effect of soil structure interaction can be seen very distinctly. So mostly the medium height structures of 10 to 12 story buildings which are on the soft sediments, so wherein like the period has been increased to 1 second to 2 seconds. So the structures could have performed well when the period was 1 second for which they are designed, but if the period has been extended to 2 seconds, they could not perform well. That's a simple thing. So that means like the wave characteristics has been changed, so that the duration in this particular event at that particular location, because of interaction of such kind of soil, so the duration parameter of the input ground motion was increased, okay, not the amplitude part. So this is the same thing, Hansen Expressway, you can see here. So this is intact part of it, and part of it completely collapsed. You can see the change, or the pattern is so different, failure pattern or the damage pattern, and the intensity is so different. one place, it's intact, other place it is like completely toppled down. So, but this might be same design with the same, pier foundations, etc. So you can see the kind of failure that happened. This is because again the period of the ground motions was increased from 0.65 seconds, for which it is designed to 0.93 seconds. Okay, so let's see our examples, because Buzz earthquake, to be frank, I feel this is the hero of the ground motions in the country. Anyway, so this is actually some of the structures which has been seen in Ahmedabad. As I said yesterday, Ahmedabad had experienced more severe damage when compared to the Kutch region. So this is simple 4-story L-shaped building, completely collapsed, and you can see here 10-story C-shaped residential tower in Ahmedabad. So again, a lot of failures. The Kathmandu Valley. This is another classical damage studies we can do, not only for the asymmetrical structure and also the topographical features. So the structures which are on the crustal portion of the mountains or hills, whatever it is, so they didn't had severe damage. Okay, there with the moderate damage, whereas the structures that are in the valley portion had a severe damage. So these are the structures in the Kathmandu valley part. So this is a soft story collapse of RC structure. You can see the kind of damages it had, and see the foundations how they failed, and complete collapse. And this is a school building, again it was in the C shape. Okay, and there's a soft story of the frame structure as well. So this is up to the superstructure part, right? And let's see some of the failures, especially we do see with the pile foundation. See, when we have a soft sedimentary strata, obviously people go for deep foundation. So that's a pile foundations or pile raft foundation, right? So let's see how the piles behave. And during earthquake, okay, the maybe vibration in the foundation also. After that, there is a gap formation. This is a simple thing. Even if you take a small pencil and put it in a clay sort of material or any kind of soft strata, and then just to do some lateral displacement on the top, and after some time, after a few motions, then if you leave it, like obviously there's a gap formation. So after earthquake also you do have this kind of gap formation. So then if a gap is formed, that means the pile is not contact with the soil. And when the pile is not in touch with the soil, obviously how do we transfer the load? Mostly these piles are friction piles. These piles are friction piles, because in these areas where we are working on, like with the thick sediment or soft sediments, where we do have expecting soil amplification or any other geohazards. So bedrock is very far, so mostly that means that these are all friction piles. So you see here, these are not columns, they are the piles. You may be surprised like what happened to the soil around, because pile should have embedded in the soil. So it has been completely washed out and lateral spreading. So it is liquefied, and then just because of the it's a topo details or whatever the variation in the topo, so the material has been completely washed away. So because of that, you can see the kind of failures in the foundation as well. And see this at the connection between the pile and the pile cap. Okay, whatever it is might not have done properly. So because of inadequate connection details, so there's a failure, because the connections are the most weakest parts, right? And this is the flexural shear failure of the pile, and this is again during the 1989 Loma Prieta earthquake. So whatever problem here is, like you have seen the failures for the superstructure, especially when they are asymmetrical, and we have seen that on the pile foundations, right? So what we are trying to do is, like, how do these asymmetrical buildings which are supported on the pile raft, because pile raft is something very, very, we don't have a IS code right now for pile raft. We do follow Paulo's papers or the book, so for design of it, but it is something very, very fastly adopted in the country for high-rise structures, wherein, like because it saves a lot of money, because these two, we are taking the advantage of both the types of foundations. Like raft is the mostly load bearing, and pile is a settlement reducers. So in such soils, maybe we do have differential seismic differential settlements, so that can be handled by piles. And since there is a lot of inertial forces do come because of seismic activity, so that can be handled by my raft. So that's where, like there's advantage of this pile raft foundation system. So, so coming back to this, to address this problem, what we have done is like we have considered our problem as a asymmetrical building, and that to geometrical asymmetry we have considered. And then because these are the common type of asymmetrical buildings that people build it in most of the areas, especially in Gujarat or in Delhi or any other seismic area. So what we have done is like we have considered these foundations are on the pile raft, and then started working on understanding the behavior with the different kinds of soils and different kinds of layering and different kinds of soil properties, especially shear strength parameters and earthquake ground motion. So we started looking at which are the most controlling factors in the overall response of this dynamic soil structure interaction of this particular problem. So for that, we have developed our code, as I said, like it's a finite element model. So first we have to define the problem by giving the geometrical details, meshing, then assign the material properties, boundary condition. For boundary conditions, we have taken the observing boundary, and then once we have given this nodal loads, then we have to define the interface nodes also, because interface element modeling was not done before that, which we could incorporate in our thing, because as I said, like the pile, the soil around the pile are mostly interface elements. Okay, they're not having the same property as the soil, which is 100 meters away, because in this analysis the boundary of the soil boundary, we do take 200 times of the width of the foundation, so it is like larger area. So then we define time step. For each time step, it will, the data will be passed to the explicit and implicit solver to calculate the responses. Responses are in terms of stresses and displacements at every node, and we will check it up whether it is converging or not. If it is not, again it will go to the loop and do the analysis again. So this is actual, this part, that A part, wherein like actual analysis do happen. This is the algorithm for that. So wherein like you give the acceleration, then it calculates velocity and the corresponding displacements, and it will see whether these nodes are in contact, so or not. If they are in contact, then it will calculate the total displacements at that particular node. If not, again it will recheck that. So coming to the details of the numerical model, so we used 8-noded brick element, that is raft, soil, or the pile. For 2-noded brick element for beams, columns, and the superstructure. So coming to the modeling techniques, so we use node-to-node contact and column raft joints. So we made it as like columns are completely embedded in the raft, so which is mostly as a rigid connection. And soil, as I said, like we considered observing boundaries. So wherein like a wave passing through will not have any reflected part of it. It just pass by, because waves are passing through any boundary. If you don't consider it as absorbing boundary, there may be possibility of reflections, and other parts of the reflected part of the wave can come again. So to make the problem simple, so we generally assume that as an absorbing boundary. And then this is how the program works. So you do give inputs in txt files, like geometry, nodes, and elements, contact details, boundary conditions, material properties, and constraints. Then load data with respect to DOFs, and then it Dyna, so that properly can be plotted. So as I said, like when you develop any model, okay, numerically, so without validation, it's of just no use. So validation is such a crucial part. So we do validation. We did, as I said, we did using the already available data from the literature. So Hukamabadi, what he has done was like he has done both experimental using shake table. Then again he has done using numerical through flat. So these are the data details of the different kinds of things that he has taken, like foundation details, engineering properties, and the piles and the superstructure details. So we have considered the same thing from his published work. And this is our finite element model for validation. So he has used the same 45-meter structure which is on the pile foundation. So this is the details of the structure, and we model the same thing which he has done. This is actually the scaled down model that he has done in the shake table test. So the same thing we have done, and he used the 3 different ground motions, like 1994 North Ridge earthquake, Kobe, 1995 Kobe, and 1940 El Centro. So these are the details of the ground motions that he has considered. So the same ground motions we also adopted because we need to validate our model. And these are the comparison or the validations which we have done with our finite element model with the available literature. So this is actually that thing. So they use FLAC as well, and also the experimental part. So our thing is our finite element model that is here. So this is for the different ground motions. We try to compare how the experimental versus our study. So you can see here the different ground motions, because we just want to understand the validation. When you want to carry out validation, you have to consider all the parameters same as they have done in the experimental or with the FLAC. So then lateral displacements with our study. So this is a comparison of the displacements in terms of with respect to their experimental and the FLAC analysis. So when we see that experimentally, our code is like almost like 10 to 17% variation, whereas numerical it was just 5 to 8%. So wherein like very much acceptable. So this is actually with the commercial FLAC. So we thought like it's fine. Only drawback at that time was like the computation time was very huge. So it's taking so much time for one model to run. That was the major drawback we had at that time. Anyway, so then to start our own thing after validation, we have started with 3 geometrical asymmetries, L shape, C shape, and T shape. And then for comparison sake, we have considered a rectangular building, which is generally common. Okay, and all the structures are having the same plan area, so 27 square meter, and 10-story height. So all the buildings, what we did, it has been designed for pile foundations, considering the actual structural loads. So after we have carried out the complete design, so this is the data of the different parameters like soil, structure, pile, raft, its Poisson's ratio, friction angle, C value. So these are the parameters that we have considered. And coming to the damping for soil, we have considered hysteresis damping, and for other superstructure and the substructure, we have used MPT. So this is the data that we have used for our analysis. And then we want to start with our Buzz earthquake. But Buzz earthquake is actually we can't give, because as I said, the computational time was taking so much. So what we have given one second. So what we have given is like only the major part of the ground motion we have considered. So because the model is taking a lot of time. If I given the entire ground motion, it takes so much cycles, and then it takes a lot of time for the analysis to complete. So what we have done is like only the 15 seconds of the this predominant ground motion only we have given as an input. So we started the analysis. This is for the L building. You can see here, as I said, like 10-story height, designed the piles for it, and then started the analysis. Similarly to the T and C also. So to start with, so we have started with, general thing, starting without any SSI fixed base condition. Obviously, there is a difference. So we have to carry out SSI analysis. And then, when we did this one for response comparison, so we have considered the rectangular building, and we have started noting the X displacement, Y, Z displacements at different nodes in the building at different story heights as well. Okay, this is at the top. Okay. Top of the structure at a particular node. So at different nodes, we try to see the response so that we can understand which is the more critical node in a particular symmetrical building aspect. So, so many results are there because we have started comparing the response, all the three direction response at different nodes at different story heights. You can see here, this is for a C-shaped building in X direction at different heights, like at the ground floor, like to the top floor. Okay, so how the X displacements are varying. So we try to understand, like, how the overall behavior of the superstructure is happening under this particular conditions of analysis. So this is actually the response comparison in the principal direction. So we, for this L-shaped building, we assume that we got it like node A is most critical part, and these are the displacements both in all the three directions X, Y, and Z at node A. So similarity that similar to the superstructure response, we need to understand the raft response and the pile response as well. So what we have done is, like, this is for the raft response again in all the three directions. So pile response, pile, what we have done is, like, at the tip, that is at the connection between the cap, that is raft, and the pile, this pile head we call, and the center of the pile, and at the bottom part of the pile. So we want to see how the displacements are varying along the length of the pile in almost all the three buildings. This is for the C. So also we can calculate the settlements. So when we try to compare, because there are so many responses in so many directions, in three directions at different nodes and different heights, so we would like to converge that. So this is the superstructure response at the top of the structure, and for three different buildings. And when we compare that with the regular standard rectangular building, and when you see here, you can see here, mostly, C-shaped buildings are giving higher response when compared to the other two asymmetrical structures we consider. So to conclude from the first part of the analysis, so the numerical code or the implementation of this DSSI problem is really very challenging. I think a student has really done extremely well in developing her own model. So it was very challenging, and it also, because we need to incorporate several complexities, like, interface effect, which we have adopted here and in our model, and earthquake and viscous boundaries, and structure foundation joint treatment, and soil nonlinearity, okay, through the material model. So we could consider all the complexities that are involved with the DSSA analysis. That's why the code results are very much closer to the experimental or the FLAC analysis in the validation part. And the validation was maximum ranging from 6 to 12% variations, so which is very much on the safer side. And we conclude that the proposed numerical soil structure code is a valid method for simulation with sufficient accuracy with acceptable limitations. So we also observed that this is, like, taking so much time. The numerically, it's very computational capacity was not that higher. As I said, initially it was taking 93 hours just to run one model. So like, you have so many different combinations to understand, to run, so that we cannot complete the work in the whatever 3 or 4 years. So that's why what we have done is, like, we decided to improve the computational efficiency first. So I'll explain you how we have done that. And then displacements are higher when the interaction effects included in the analysis in almost all the directions, obviously, because we have considered the overall effect of the soil substructure and the superstructure. And the X response is found to be more, which is almost like 15 to 20% in case of DSSA analysis in all the three directions. Difference in the response is lesser at the lower levels of the superstructure when compared to the top layers at critical nodes, especially when we observe. Coming to the effect of asymmetry, so what we observed, rectangular building is showing lesser response when compared to the other asymmetrical, obviously, because symmetric plays a major thing, especially in terms of seismic resistance. So then the C buildings are having higher when compared to the rectangular, and of course then L and T buildings are also having almost like 20%. So the foundation lateral displacements and the settlements is nearly same for all the buildings under the same earthquake load. This is one of the interesting observation. We can say that the foundation part, okay, irrespective of the superstructural asymmetry, so the lateral displacements and the settlements are not having any variation. So I think this is one of the very good outcome of this particular analysis that we got it. So the structural hazards are more associated with the structural asymmetry, whereas the foundation part is not responding differently for different superstructure asymmetry. So as I said, like the code is taking huge amount of time, so we need to improve the efficiency of it. So what we have done is like we have started, so there are n different number of piles that we got it after the design of different structures, right? All the 4 different structures. So what we have done is like we want to adopt this equivalent PM method. So this has been proposed by Paulos. So what it says is like, you can consider a single pier which is equivalent to the n number of piles that are there supporting a structure. Okay, so there is a standard procedure for calculating the equivalent pier diameter. It's material properties, everything. So like Young's modulus of this EPM. So this is what we want to adopt, so that rather than n different piles that are there to model, and we have only one pier, so that your computational time can be efficient. It can finish the program quickly. So then there are, like, when you want to adopt a EPM approach, so there are different ways. Like this is how it is. You have a L-shaped building, and whatever the participating piles in this particular zone, you can model it as a one single pier. And for this zone, another one. For this zone, another one. Since it is like all 3 are equal, so we have 3 different piers. Okay, if we assume this part as one area, whatever the piles that are participating in this area can be modeled as one equivalent pier. And for this one, so which one to adopt? There are, like, this is, if you see here, this there are 4 different ways of EPM. This is 3rd one and 4th one. So I can consider the entire piles, all the piles which are participating for a L-shaped building, and model it as a one equivalent pier. So which one to follow it up? So in the starting, we want to understand what is the the effect of EPM methods also. Like just let's see, like one L-shaped structure, assuming that one a particular asymmetrical structure, so with complete all n number of piles and all EPM 1, 2, 3, 4 methods. So let's see which one is more closer to the general configuration of n different piles. So that's what we want to observe. So then we have done the calculations for all the 4 EPMs. So these are the, like if you see here, this is the first 2, 3 areas for the 1, 2, 3, and then for each area, of course, L and B. So then number of piles participating. Then we will be calculating the equivalent pier properties. Okay, and its location can be calculated. Then we can model that. Okay. Similarly for this EPM 2, EPM 3, and of course EPM 4. So these are the different EPM models. So again, started the analysis. So this is the response for the first EPM model at the critical corner. As I said, like for L-shaped building, this is the critical corner. So rather than observing at all nodes, so what we decided is like just to understand the behavior at the critical node at different depths. Okay. When we started comparing this with different EPMs, okay, 4 different EPMs that we adopted with the general configuration. So these are the displacements in principal direction with then we understand that percentage displacements in 3 different directions. So these are the 4 EPMs are giving with the when we compared with the general one, right? So the same thing, analysis time also we need to compare, because the idea of adopting EPM is to reduce the computational time. This is the analysis time when we adopted 4 different EPMs. So if you see here, CPU time, this is 51 hours for L-shaped building for this particular analysis, whereas EPM 1, 2, 3, and 4 were giving 20, 17, 18, and 15 hours. So when we see that number of elements also, because it's reducing, right? Because it's reducing, so number of nodes are reducing, so the computational time is also reducing accordingly. Similarly, other two symmetrical buildings like C and T also, these are the different TPMs we adopted. And then we started doing the analysis. So these are the analysis. So these are the attributes for the pile configurations, and with equivalent peer dimensions and location and other things. Then after doing or after achieving this computational efficiency, what we decided is like we'd like to do the parametric study to understand which are the more controlling factors, especially when it is coming to DSSI. So because I'm from the geotechnical background, so I'm more interested with my soil part. So we started looking at 3 different soils, like completely C soil, Phi soil, C5 soil. Which one? And give you kind of better response, I can say, at least to have understanding. Then another one we want to see with the different ground motions, because in this one what we have considered is like we have considered 2 Himalayan earthquakes, like you can see Chamba 1995 Chamba earthquake and 1999 Uttarkashi earthquake. So we have considered 2 Himalayan earthquakes. In addition to that, we have taken one Bhuj earthquake. So because Bhuj is something which is so important, because it happened, and so it's such a big eye-opener sort of thing. Then Lbd ratio of the piles also we have tried to understand, because in geotechnical design it's not like structural design, it's not a prescribed kind of thing. So you do have a lot of judgment goes in, and if you give the design to two people come up with the 2 different designs. That is possible. So especially with foundations, etc. So that's where we want to understand the different Lbd ratios. So with 10 to 50, we want to see how the response of the superstructure, especially considering the SSI. So these are the soil properties for 3 different soils: SSI, C soil, Phi soil, and C5 soil. Now started our analysis to understand the displacements of different nodes for different structures, all the 3. Okay, these are the overall results of the analysis result. So this is the superstructure response, this is the pile response for 3 different soils, C5 and C5. Actually, later we have put it up, this 2015 Nepal ground motion also, which I am not putting here. It is published in Journal of Asian Earth Sciences. And then this layered thing also, here we started with a homogeneous soil, like completely C soil, completely Phi soil, or completely C5 soil. Then we started looking at 3 different layers of 3 different properties, 3 different thicknesses, and see, you can play now with the changing in the different parameters and trying to understand that. So when we see this, you can see C building is having higher response in almost all the 3 different, all the 3 soils, S1, S2, S3, when compared to the corresponding L and T. So to see the effect of this supporting soil types, that is 3 different soils that what we consider. Peak displacements, they are varying in the range of 12 to 15% for these 3 different soils, S1, S2, and S3. And whereas the soil, that is C-type soil, S3, they are showing more transfer of vibrations to the superstructure than compared to C5 and the Phi soil. So this is one of the very interesting, takeaway from this analysis. The same observation has also been found for the remaining 2 T and T type of structures as well. Then C building response was higher. In almost all the analysis, what you do observe here is the response of the C buildings are much higher when compared to L and T, with almost all the change of parameters. Okay, you change anything, but the C response is higher. So that means the geometrical asymmetry is very strongly controlling the overall response of the superstructure. But the superstructural asymmetry is not controlling much the foundation response. Okay, whatever the asymmetry of the superstructure, the foundation response is completely depending on the substrata. So then more than L-shaped building, and which is almost 31% more than T-shaped building. So the response of the foundation, overall foundation, that is including pile and the raft both, it's ranging from 4 to 9%. So this is the 3 different ground motions we have considered. We have specifically consider two different Himalayan earthquakes. Why? Because if a strong event happens in Himalayan seismic gap, there is a huge effect on most part of the Indo-Gangetic plain. So because of this far field effects. So Himalayan earthquakes are not only hazardous to the regions of in that region. There is even they can be felt even in parts of Bihar, Delhi. They are also having the hazard because of this far field effect. So that's why what we want to understand is if an earthquake happens in Chamba, okay, if I have a asymmetrical such kind of building which is on the pile raft in Delhi, okay, how do that behave, right? How do my structural response will be for a far field earthquake rather than near field earthquake like Bus. Okay, so this is the idea of considering this part. As I said, later in 2015 we had this Nepal earthquake. Then we incorporated Nepal earthquake as well, because that is another typical event. As I said before, Nepal earthquake, it has a strong topographic effect, okay, because of the valley thing. So that has been incorporated. Of course, that's not updated in the slides, but it's the published part. So these are the details of the ground motion with the predominant frequency, focal depth, and the epicenter details. So again, when we did the analysis, so this is the response of the superstructure, three different directions, X, Y, Z, again at three different nodes. So this is the overall results, building response for three different ground motions. So when we try to see the response of the superstructure Bus earthquake, because it's a near field effect, it's having higher response, 52 mm. Of course, you cannot compare two different earthquakes. Okay, so even the earthquakes of same magnitude, you cannot compare. Okay, so there is nothing like comparison. Only thing we are trying to understand in this particular analysis, effect of far field ground motion thing on symmetrical building. That's all. So pile raft, it varies from 11 to 5%. The same observation has been made for the two structures like L and C shape also, building with a different peak responses. So for all the ground motion, C buildings are giving more response than the remaining two asymmetrical structures which we have considered in this particular study. Then the last one, effect of Lbd ratio. So as I said, a lot of judgment goes in the geotechnical design. So what we did is we started varying the Lbd ratio from 10 to 50, and then again carried out the analysis. So lateral displacements in the piles. This is for the C-shape building. You can see as the Lbd ratio is higher, the lateral displacements was observed also higher. Okay, so this is very distinct observation. We could make it up. Similar thing we have seen even for the other two buildings, also similar response, L and T. So this is the overall analysis at the center of the pile. So X displacement, Z displacement in the superstructure, whereas pile response lateral and the settlement. So for all the three different buildings, and varying the Lbd ratio. So CLT and Lbd ratio from 10 to 50. You can see here as the Lbd ratio is increasing, obviously the displacements are also increasing. So to conclude from this part of the analysis, so for larger diameter, the displacements found to be less. Okay, that is which is the Lbd ratio of higher lesser value, whereas the smaller diameter piles, okay, the response is higher. So that diameter is less, Lbd ratio is higher. The pile length in contact also contribute to the developing of the contact displacements. That is, the contact area for Lbd ratio of 40 is less than 20 and 30 respectively. So the pile soil interaction, they contribute in the response. So that is observation we can make it from this. Then the least response was observed when the Lbd ratio was lesser. Okay, that is the pile diameter is higher, and for diameter less, Lbd ratio higher, we got the higher response. So the maximum response was found to be 32% more for C-type buildings, and then the T-shaped buildings followed by T, and then later by L. So that means that the geometrical asymmetry it altering the response for different Lbd configurations also. So with this, I just come to conclusions part. So the overall conclusions from this particular research part was the code, the numerical implementation of the dynamic soil structure interaction problem is really very challenging and interesting as well. So only thing is like you should have a strong mathematical background and little bit coding knowledge. So that's all. So and the DSSI code shows good agreement with the experimental and numerical. See our results like not only that validation with the published literature, even like we after this we started a little more work in continuation. Considering the Nepal earthquake, because Nepal earthquake, the specific, C-shaped building which has been completely collapsed, which I showed you in the photographs. So that has been considered, and of course we assumed some material properties. It's not like we have the actual material properties of the structure. So we started understanding the damage pattern, like do the analysis and how to simulate the scenario of the earthquake, right? So that was also that's a small piece of work which has been very interesting part. And the effect of interaction in analysis, it alters the system characteristics and the overall response of the building. So then the asymmetrical system is different from the symmetrical configuration, and this the whatever the degree of asymmetry that is associated with geometry, it is actually controlling the overall response of the superstructure. So we have to be very careful when we considering an asymmetrical structure, whatever, either geometrical or load asymmetry. Of course, we didn't consider load asymmetry in this particular analysis. So because shape asymmetry is something which was seen very, very common. And EPM model, whatever we adopted, it proves to be very, very numerically competitive. It saves a lot of time. And the interface effect can be made robust in the EPM model, because rather than modeling n different files, I just model one single one. So it enhances the simplicity of the complex DSSI code, and accuracy was acceptable, of course, in a relative terms, that it can be applicable for the asymmetrical pile group. And earthquake characteristics, soil characteristics, foundation geometry, they are playing important role in the overall system response. So with this, thank you so much for giving this opportunity. If you have any queries, I'll be very happy to answer.
Thank you very much, madam. Madam, I have 2-3 questions.
Yeah, please.
Madam, first of all, is there any displacement limiting values for a particular story height for top story basically?
For our analysis, we didn't consider any limiting value. We didn't consider. We just want to know the response, right? So that's why we didn't consider any limiting.
So madam, how we can say that this particular building C-shaped or L-shaped will fail at a particular displacement value?
That the overall displacement part, that depends upon the country building code, right? The limiting condition, and that too the comfort of the even the building is safe, it cannot sway, right? If it sways so much, the comfort level goes down, and people may not feel comfortable, right? Even during the earthquake. So that depends upon the particular country seismic code or building code, whatever. Coming to the second point, stability issue. One is like that convenience part, or like from the psychological perspective, and the second one is structural stability issue. So what we looked at is not on the psychological part. We were looking only on because that depends from country to country. Okay, code to code. So we were only looking at the structural part, and in this particular analysis, the main focus was like which parameter is the more controlling parameter in overall building response. Building response is taken not just in the displacements part, even with the stresses part, because there is a lot of values, because at every node, every height. So when we are getting the response, it is not easy to compile it. So that's why for understanding sake, stresses were also been compared. We have considered this displacements, for showing the results.
Madam, second question is, which software is more suitable for surface soil interaction, means structure surface interaction?
People commercially, there are codes available. Dssi is there, FLAC is there, but they're quite expensive. Okay, and that too, you can use that when you have a kind of industry consultancy sort of project. People prefer to use that because it saves time. But for us, the constraint at that time was like, I don't have money to buy it at the time. Second thing is like, we want to develop a simple code where we can, see what exactly it is happening inside. Okay, it's not like a black box sort of thing. So that's why we started with this. Yeah, I think we could achieve something.
Ma'am, actually, we are doing on SAP or ETAP. So what we consider that let assume it is a fixed foundation is a fixed, and then we will check the stability of the structure. But
You cannot fix the foundation. Actually, when you design the pile foundation, there is something called fixative factor. Okay, this is a common question which comes from the industry. Fixative factor, people consider based on their experience, 60% or something, but you cannot fix it to 100%. You cannot never, you cannot fix at all. The fixative factor cannot be 100.
so madam, is it possible to
Even if it is
model?
anchored into the rock.
Yes.
Even if it is anchored into the rock, you cannot fix it because see, even the ground, I think, microthermal testing and other details Swati can explain after this lecture.
Yes.
Ground is always under vibration, which we are not able to feel. There are micro vibrations, always it is going on, so which we are not able to sense it. But the thing is like, when ground is always in vibration, micro vibrations, how can I fix it, right? It's nothing like a fix it.
So, madam, is it possible that time history that we are taking on structures, we are taking it on surface only. So we can use directly to a structure.
Yeah, that's what I was telling yesterday. You have to bring, you will get it from the seismic station data, you will get it at the bedrock. You have to bring that to the surface. Okay, if your instrument is at the surface, you can, that's fine. You got it directly measured from the surface and you can put it. Okay, so whatever it is, but the effect of soil which is there above bedrock or above engineering bedrock, I can say, because bedrock is not easy to find everywhere. So above engineering bedrock is something very crucial because that is the most controlling parameter for your damage. It's not actually the superstructure. It is more because, as I say yesterday, it's not like I'm a geotechnical engineer saying this. No, it is actually the true part of it. So I personally feel that people ignore the behavior of material that is soil because it is complex to understand. If it's complex to understand you, I just ignore you, right? That's the easiest part. I can do it. So people are doing that because it's highly particulate, highly granular, material behavior is highly non-linear, hysteric. So you cannot, easy modeling or modeling soil is also very, very difficult. Okay, and the superstructure part, it's a continuous, uniform, and it's in my control, right? Material properties are under my control. So that's why it's easier. So, and that, whatever it's buried below, people are not able to understand what's happening exactly until unless it fell down. So that's why this area itself is very, very new. I mean to new in the sense 20 or 25-year-old, because it all started with Buzz earthquake, at least in the country. Okay, before that, people were not even aware what is liquefaction. Even some in our geology textbook somewhere, definition was given. So we are not even aware. No analysis. How to analysis for liquefaction was not clear. So now, like we came to a better stage where like we have our seismic code guiding us, and for all projects, we have been asking to do this dynamic soil property at field tests, especially MSW, such kind of tests are compulsory. And people are asked to carry out, liquefaction analysis if it is in seismic zone 4 and above. So at least like, in the last 20 years, with the efforts of the government of India through the research projects, I think we grew to the better, understanding level. I think more need to be done at the industry because they are the people who are actually doing it, right? So we do research, we publish it, but this whatever the published, it should go to the field. It takes a lot of time. Whatever publish research, it comes to a textbook after 20 years. So then we don't have time for it, right? So it's simply whatever, it should immediately go to the practice part. So that can happen only through the events like this. So I'm very happy with Dr. Amit, who is really active. I didn't see any institute, so active, at least in Indore, who are doing multiple activities all the time, discussing something technical. So I'm very, very happy with your way of, working at IPS.
Thank you, ma'am. Thank you very much, ma'am. And we need your support throughout the time, ma'am. One
Please
more
do
question is
something for
there, ma'am.
that student chapter.
Yes, ma'am.
Please, you already
We
have students. Please do that IGS student chapter thing.
yes, ma'am.
Yeah,
Sure,
you
ma'am.
have one more
Ma'am,
question, please.
yes, ma'am. Ma'am, this is from one more question there. Is there any free software for students for DSSI?
I don't know. I really don't know. I didn't check for it. No idea.
Madam, one more thing is there. Right now, we are having uniaxial check table at our heavy structure lab.
Hmm.
Now, very soon we are getting biaxial check table also.
Oh,
And
that's nice.
what I understood right now is that we can give the input in terms of force and displacement.
Okay.
So, can we do something related to surface soil interaction
I
by
mean,
using our
actually,
biaxial check table?
last time, we discussed about this, right? Someone, your colleague who wants to do PhD can
Yes,
register.
sir.
But, your institute should also sponsor it, right? In
Yes,
that sense, see, Monica is doing from this, what is that university?
Yes, sir. Yes, ma'am.
RDP.
Monica Daniel.
Monica, I think is here, right?
Moni, Monica, madam.
Monica
Monica.
madam, yes.
So Monica is doing her institutes have sponsored her. So
Yes,
similarly,
ma'am. Good morning.
Monica, hi. So she
Yes, ma'am.
already started working and almost 1 year. She has a very nice paper also recently got accepted, which is having more than 4.3 impact factor. So of course, hers is a experimental thing, which is she's working on environmental geotechnics. So I don't know, how it works with your university, but if really there is somebody who is motivated to, work, so I think no issues. I can take that, but they should work because Monica travel almost like too far, and she comes whenever I ask her to come.
Sure, ma'am, we will do that, ma'am.
I think couple of them that time long back, from your university, they approached me,
Yes,
but
ma'am, we came along with our MTech students also, ma'am. But after
actually,
COVID, actually, most of
then,
the
yeah,
things have been
COVID has
changed.
changed
Yes,
many of
ma'am.
our plans, etc.
Yes,
No
ma'am.
issues, that's okay. But if there is any student, even like you can interact with other institutions also. Like, Amit, if you're really interested, why don't you interact with Monica? She's also keen.
Sure, ma'am.
So you can across the institutions also you can think of something, right? So I think at least some good institutions are around. So yes.
Yes. And actually, madam, our heavy structure lab is open for all the researchers. They can
Hmm.
come and do their research work. No issue, ma'am. Our principal madam has given permission for that.
Sure. You see, if any of your faculty colleague is looking for PhD and if they can be sponsored, just check with Monica how she has done. So she can guide better because she went through that process. So let's see how we can work on that.
Yes, ma'am.
If you have
Sure.
some facility at your institute, that will be great. They can work there only.
Thanks, ma'am.
Okay. Sure.
So thank you very much, ma'am.
Yeah, thank you so much. And thank you so much again. I have a couple of things. Internships are available, so online hai abhi to. So please,
Yeah,
if whoever are interested, they can contact me. Okay, I can link with some of my students as well. So
sure.
mostly right now we are working on numerical part only, especially with the internship students, modeling aspects only, not experimental. But hopefully soon the campus will be open. Monica is asking like to allow her students for quite long time, but still like because of the COVID protocols in the campus, that could not happen. But maybe hopefully when it comes, like, I'll be happy to host you. So thank you so much again. Thanks.
Thank you very much.
Thank you, ma'am. Thank you, ma'am.
Thank you so much, ma'am, for this wonderful session, especially that you shared your knowledge, whatever you had done in the practical work. That's really appreciable, ma'am, because people don't really agree to share their experiences as fast as you did. Thank you so much, ma'am.
Yeah, thank you so much. So when is the Swati's lecture starting? 11:30, yeah?
Yes, ma'am, at 11:30.
You can ask her to start if she is ready.
Sure, ma'am.
Ma'am, good morning, ma'am. I'm
Swati, you
here.
are there? Acha,
Yes,
okay.
ma'am. I
So
thought.
madam is there, we can start, madam, right now.
Okay, I just want to hear to her as well.
Yes, ma'am.
Okay.
Going to defend soon. Thesis ka, few reports
Yeah.
came, and so yeah.
Sure, ma'am. We'll start right now.
Good morning, everyone. Actually, before starting this particular session, I just wanted to answer a query. Like, is there any free software for students for DSSI? What is this? OpenSeas and OpenSeas PL and a few more open source softwares are available, but they are included with they are into with coding. Actually, you should have some coding knowledge in order to do some sort of problems with that OpenSeas and OpenSeas PL. So if any student is there, like, it will be helpful for them to search for that and do some analysis in that. So I just wanted to answer this query. Even I am not into these softwares, but I have heard it from my fellow researchers actually. So now today, to start with my session, it is I am
Ma'am,
to, yes, sir.
Ma'am,
ma'am,
we request you to please give us a chance to introduce yourself, ma'am.
Yes, thank you, sorry.
So we are at the second session of this day two of 1 week online faculty development program on new approaches in geotechnical earthquake engineering. And we are glad to have with us Swati Priyadarshini Putti ma'am, who is a senior researcher in earthquake engineering at the Research Center, IIT Hyderabad. She is pursuing PhD under supervision of Dr. Nilima Satyam ma'am, who has just taken the section. And her research interests are earthquake geotechnics, liquefaction studies, dynamic site characterization, seismic microzonation studies. We are honored to have you with us, ma'am, for sharing your knowledge and work. And we are thankful that you could take out time from your schedule and enlighten us over this very major issues that are addressed in the faculty development program. Thank you so much, ma'am. And I request you to please take over the session now, ma'am.
Yes, ma'am. Thank you so much. Can I request for this access to share my presentation?
Yes, ma'am. Yes. Ma'am, is it active now?
Yes, thank you. Yes. Today I am going to discuss the applications of dynamic site characteristics and as well as seismic hazard assessment in earthquake geotechnics as well as in geotechnical engineering. Okay, so first of all, I'll let you know why I have combined this dynamic site characteristics as well as seismic hazard assessment both in a single point. See, actually, seismic hazard in a particular region is dependent upon many factors. Okay, so like the tectonic activities which happened previously, as well as the faults which are there, either they are active or not active or reactivated recently. Some faults may be they are not active for a particular long period of time, like 100 or 200 years, and after that they'll get reactivated and they'll have some seismicity. Okay, they'll increase the seismicity of that particular region. So like seismic hazard of a particular area depends upon the tectonic activities, whatever the faults and other sources in that particular area, and the local site conditions, that is dynamic soil characteristics. Local site conditions, nothing but dynamic site characteristics, as well as the stratigraphy of the soil. So that is why like the seismic hazard entirely depends upon the local site conditions. So that is the reason I have combined both the dynamic site characteristics as well as the local site conditions, that is dynamic site characteristics. Okay, so here in this presentation I am going to like briefly give a case study of Vishakhapatnam. Okay, we have done dynamic site characterization for a study area Vishakhapatnam. Like most of you have heard Vishakhapatnam port, which is the second largest port in India. And so as this is a port city and one of the most important cities in the particular region, like Andhra Pradesh, we have chosen this particular city as a study area. And one more main reason why we have chosen this study area is we all know that most of the South Indian part comes into zone 2 and zone 3, which is of low seismicity. Okay, but why we have chosen this particular study area, which is in zone 2, is recently the seismicity is getting increased in the Eastern Ghats region. Eastern Ghats Mobile Belt region, that is the coast of Bay of Bengal, the entire coast of Bay of Bengal. So as this study area is located in that particular region, we have considered this to study as it is one of the like there is increasing seismicity. Okay, so and the significance of this seismic hazard studies as well as the local site effect studies are like hazard will be quantified nearest to the reality. We already have IS code which is giving the macro zonation part. Like the entire South India is just divided into two parts, like the zone 2 and zone 3. Like some locations are into zone 2 and some locations are into zone 3. That's it, right? But whenever it comes to the reality, like the pinpointed, like site specific studies, the like the seismicity may be increased. Whenever we calculate the dynamic site characteristics, the seismicity is an increased pattern when compared to the Indian seismic code, as it is micro-zoned. Okay, so that is why we'll be choosing seismic hazard studies. That is, the hazard can be quantified to the nearest reality, and this also yields the responses of the soils accurately. Ground response analysis and site specific characteristics, local site conditions, which are discussed by Neelima ma'am, all these are like to yield the accurate response of the soil in that particular area. Okay, and which ensures the better safety and serviceability. Okay, so in this study you will be seeing like how these dynamic site characteristics are different from our codal provisions. Like we have what we have observed in the study is the region is having increased seismicity when compared to the values given in the IS code for zone 2. So that is the main reason this site specific studies and microzonation studies are really important for structures, whatever the geotechnical problems and all. Okay, so that is why we have chosen this particular study area, which is already in zone 2. And here there are two parts in the study. The first one is dynamic site characterization, and the second one is how we are going to use or how we are going to apply dynamic site characteristics in our realistic problems. Like we have chosen a port structure, that is a pile supported wharf, which you can see. Sorry, one second. Yes, pile supported wharf in Vishakhapatnam area, and this pile supported wharf, as you can see a schematic diagram here, this pile supported wharf which is damaged during 2004, that is Great Indian Ocean earthquake. Okay, so this is damaged during that period of time, like they are having high tides in Vishakhapatnam port as well. So at that time this particular pile supported wharf is damaged, but as there is no knowledge of earthquake geotechnics and more of like liquefaction studies at that particular point of time, the exact reason for the failure of this particular pile supported wharf is unknown. So we have chosen that particular wharf, and we have done dynamic analysis on that wharf using the dynamic site characteristics which we have found earlier. Okay, so this is just the flow chart, like how we are going to use, how we are going to find out the dynamic site characteristics and how we are going to use it practically. And these are the details of the study area, like Vishakhapatnam urban, and we have taken around 300 kilometers radius around Vishakhapatnam for doing seismic hazard assessment. Why? Because there are a lot more small ports around this 300 kilometers radius of Vishakhapatnam, and moreover there are a lot more faults which are highly active and which can be potentially causing any earthquakes in the future. That is why we have taken 300 kilometers radius of area around Vishakhapatnam for seismic hazard assessment. And the type of the soils that are mostly available are sandy soils, actually as some marine beds are there, marine clay beds are there, gravelly soils are there around. Okay, so yes, as you can see in the map here, this is the particular site, and what are the potential faults that are around that particular site. F1, F2, F3, F4 are the faults, potential faults that can cause earthquakes around this particular study area. Yes. Now coming to the seismic hazard assessment, before going into the details, I just wanted to let you know, we have two types of seismic hazard assessments. One is deterministic seismic hazard assessment, and the other one is probabilistic seismic hazard assessment. Okay. So in the deterministic one, we can only it typically assigns a maximum magnitude from a particular seismic source. Like it is a simple solution. Like we'll list out all the potential sources of earthquakes, and we'll pick one source which is having highest magnitude. That is just deterministic seismic hazard assessment. Now here the problem is, we don't know when that particular fault is going to create. Like we cannot define a particular time period there. Okay, when this is going to give an earthquake of this particular 6 magnitude or 7 magnitude. So that is why rather than going for deterministic seismic hazard assessment, we have taken probabilistic assessment, where we can exactly find out the location from where an earthquake is going to happen, and size, that is like from what of what magnitude an earthquake can happen, and the effects, like is a how the local site conditions are going to affect this particular magnitude, whether they can increase or they can decrease depending upon the attenuation relationships. Site specific attenuation relationships are given by many researchers in the past. So using those attenuation relationships, we can incorporate local site effects also in the seismic hazard assessment. And timing, in what time, like in the next 50 years or next 100 years or next 20 years. So I can define in the next 20 years, I am going to have an earthquake of magnitude 5 from this particular fault of F1, which is located in a distance of 50 kilometers. Like I can give a single statement single statement on all the details using probabilistic seismic hazard assessment. So if we know all this, like if we know what is the timing approximately, like in the next 15 years or next 25 years, and if we know what is the magnitude, and if we know what is the source to site distance, like whatever the structures you have, and what is the whatever the seismic source that is fault you have, if you know the distance and if we know the magnitude, we can design accordingly. We can go for earthquake resistant designing of that particular structure accordingly. So that is why we have chosen probabilistic seismic hazard assessment. So for this, the steps involved are first we are going to identify the seismic sources in that particular region. As you can see here, we have point sources which are nothing but the older earthquakes, previous earthquakes, historic earthquakes, and the line sources which are nothing but the faults in that particular region, whether it is a small fault or a bigger fault, all the faults. In this particular map, you can see all the faults in that particular region. Either it can be a fault or a lineament or a not active fault, a reactivated fault, all the faults, as well as the point sources. Point sources means historic, previous earthquakes. Okay, and all the sources we have taken. So after considering all the sources, we have to we have to go for seismic data completeness analysis. See here, the problem is like if whatever the data you have is not complete, the results which we are getting are not reliable, right? So here the main problem is the seismic stations, like whatever the seismic stations we have in India are not in working condition. All are not in working condition. First point, that is the main problem to record a particular earthquake, whether it is a major one or a minor one. Okay, so all are not in working condition, and when we get the earthquake data, like whether it is IMD or USGS or some other source, like we will be getting repeated repeated sources, like an earthquake. If we take from different sources, like this earthquake will be in all the sources and we will be listing it 3 times. So whenever we are collecting earthquake data, it is a bit difficult to filter the data and to get a proper to get it in a proper line. So in order to know whether the data we have collected is a complete one or not, we are going to do a statistical analysis that is called a steps method, steps analysis. So from that we'll know if the data is complete or not. If my data is complete, whatever the results I get from seismic hazard assessment is are reliable, that I can use them in the in any other practical problems. And one more thing is like this PSHA is mandatory for some huge structures like power plants, steel plants, and some other industrial structures. It is mandatory to do PSHA, that is seismic hazard assessment. Okay. So after collecting the seismic sources, we are going to do completeness analysis, and then we are going to find out the regional recurrence parameters as well as the hazard curves. So this is the data. We have taken it from 1828 to almost 2017. And after that, the analysis of data completeness. As you can see here, the points between these particular times are not connected. So that means the data from this particular year to this particular year is incomplete in all aspects, like in the magnitude 2 or 2 to 3, 3 to 4 or 5. Okay, so whenever we have such incompleteness, we'll take the data set in two different two different parts. Whatever the complete data we have, we'll take this one, and the other complete data we'll be taking two different sets, and we'll be working out different in a different way. So here these are the major faults, major potential faults that can cause an earthquake, which are mentioned in this particular table: F1, F2, F3, F4 and F5, and their particular location as well as distance from the source site. Here site means we have taken the Visakhapatnam city center as a center point, and from that we have taken 300 kilometers radius. So here this particular F1 is of 154 kilometers distance from that particular center point, and this fault is of 52 kilometers length, and it is potential, it can cause a potential earthquake of magnitude 6 or higher depending upon the local site conditions. Okay, so this is the frequency magnitude distribution plot, where we can find out the regional recurrence parameters A and B. This regional recurrence parameters can be used to find out the attenuation relationships, to form an attenuation relationship for this particular region. All the PSHA results are helpful in framing a attenuation relationship for this particular region. Okay, so these are the hazard curves. From these hazard curves, it will be easy for our design engineers to study, this particular PGA is having the mean annual rate of exceedance of 0.5 or 0.6 or 0.1, whatever it is. Okay, and we have used attenuation relationship of Raghukant and Iyengar, which is framed in 2006. Why we have chosen this particular attenuation relationship is Vizag is not having any of its own attenuation relationship for that particular region. And one more thing is this particular attenuation relationship is framed for Bangalore site conditions. Bangalore, which is also in zone 2 and which is also having similar soil conditions when compared to Vizag. And it is also located in South India and the nearest most place to the Vizag. So that is why we have chosen this particular attenuation relationship given by Raghukant and Iyengar for developing hazard curves as well as hazard maps also. Hazard curves and hazard response spectrum curves. Okay, so these are the hazard maps, and we have prepared it for time period of 1 and time period of 2 for a written period of 475 years. And here, as you can see, the dark green lines and some yellow lines where you can find higher magnitudes. That is because there are some faults and lineaments that are under this particular region. Faults and lineaments are present under this particular region. That is why it is having more peak ground acceleration when compared to the other locations, which are denoted in a light blue color. So this is seismic hazard assessment. Here from the seismic hazard assessment, we got the spectral acceleration of 0.11 G, like which is close to the value of IS code value, which is zone factor of 0.1 G. IS code is giving 0.1 G as zone factor for zone 2. Here from the PSHA, from the curves and all, we got it as 0.11, which is very close. So next, I am going to discuss like ground response analysis. That is response of the soil in a particular area for a given strong ground motion. So like if I give an input of Buzz earthquake for the soil conditions in a particular area, like what is the response of the soil? Here there will be two conditions, like if the soil is very soft, the soil may amplify the ground motion. That is, if I give a ground motion of 0.1 G, it may like increase the ground motion to 0.14 or 0.15 or 0.1 G, depending upon the softness or softness of the soil. Like it may amplify the ground motion. When we have the stiff soils, it may de-amplify the ground motion. So that means like ground response is something response of the soil for a given ground motion, for a given strong ground motion. So here we have taken almost 75 locations in and around Visakhapatnam. Like as you can see in the map, 75 locations in and around, like in the city. So we have used deep soil, which is from which we can do one-dimensional ground response analysis. Here in ground response analysis, we also have two-dimensional, which can be performed for the locations with the high complexity in the geology. Like if we have more of valleys or more of mountains and all, like when you have highly complex geology, then we can go for 2D ground response analysis. So here, as in our study area, it is not that complex. We have done only one-dimensional ground response analysis. So these are the 75 locations marked for ground response analysis. So here we have given the soil properties. That is like what is the shear wave velocity in this particular, if we take a soil column, what is the shear wave velocity, what is the density of the soil, and where the bedrock is located, and what is the shear wave velocity at bedrock and all the soil strata, and where the water table is located. Water table will also have its own effect on the ground response. So where the water table is located and all. So, and here we have chosen Buzz earthquake motion, ground motion, which is scaled to 0.1 G. As you can see here, maximum horizontal acceleration of 0.106 G. That is, we have scaled bracketed duration of only 19 seconds of the Buzz earthquake ground motion is taken. The other one, the other part, after 19.98 seconds, it is excluded. Because as our site is located in zone 2, which is of 0.1 G, I cannot use complete Buzz earthquake ground motion, which may result in like overestimated values, overestimated results of peak ground acceleration. So that is why I have scaled it to 0.1 G and I have used it for my ground response analysis. And shear modulus is calculated using different correlations given by different researchers. And this shear modulus is given as an input. These are the shear modulus curves. And these are the PSA, that is spectral acceleration curves for some locations like Maharanipet, Fisher Harbor, and Sitamadara, Duvada. These are all the few locations in this particular region. So I have shown just for example few locations spectral acceleration plots, time period versus spectral acceleration. So from the results, like we have, as we have conducted ground response analysis for all the 75 locations. Okay, so I have used a triangulation method and other GIS techniques for preparing hazard maps. The main motto of our study is to provide all types of hazard maps for this particular study area, so that design engineers can easily pick values from our hazard maps for their designs. So whenever someone is going to construct a structure, an important structure in Vishakhapatnam, it is already having a few of steel plants, port area, and port structures, and many other important structures in that particular area. So whenever someone is constructing, is going to construct a particular or design a particular building, our motto is to give them all the values. Like they can easily pick peak ground acceleration at the surface. Like if I am going to construct a particular structure somewhere around here, then I can easily pick the peak ground acceleration value of 0.135 or 0.14 in this particular region, higher than 0.135. So design engineers can easily pick values from these hazard maps and can use for their design. That is our main motto, to provide all these details. So here, as we already know that whenever we go for earthquake resistant designing, many of us will be randomly picking values from IS code. Here in the study area, the IS code is providing only a value of 0.1 G. But few locations are having higher peak ground acceleration at surface, which is almost like this study area, it is having 0.16 G is the higher value. 0.16 G is the higher value. So there are few locations which are having higher ground accelerations in contradiction with the IS code. So whenever we use IS code values, we can underestimate some results in our designs. So this will be helpful. And this is the peak ground acceleration map at surface, that is PGA values at surface are mapped. And this is PGA at bedrock. Okay, so PGA at bedrock, obviously PGA at bedrock will be lower when compared to the PGA at surface. Depending upon that too, depending upon the soil conditions, site specific conditions. So this is the PGA map at bedrock, and this amplification factor, which is a ratio of PGA at surface to PGA at bedrock. Okay, so this amplification factor, if I see here, if the amplification factor is 2.1, somewhere around here, that means the whatever the ground motion intensity that is given at bedrock and that has traveled to the surface, like from bedrock to the surface, it is almost amplified 2 times. 2.1 in the sense it is almost the ground motion intensity is amplified 2 times while it traveled from bedrock to the surface. So these are the some typical results from ground response analysis. As I have already said that few locations have seen higher acceleration values when compared to the IS code. The amplification factors also ranges from 1 to 2.3. In some locations the soil have potential. Wherever there are marine clays or some marine beds, the soil have the potential to increase the intensity of the ground motion to almost double it. Okay, so the locations present in the extreme southern part have shown higher response, because all the southern part of this particular study area is on the coastal side, and there are few marine beds and marine clayey beds, marine clays, where there is higher response as they'll amplify the ground motion. And northeast and northern part of the city are having have shown lesser response because there are some sort of hills in that particular region. northeast and northern part, because of the presence of the rock outcrops, that means hills, they have shown lesser PGA, lesser response when compared to the other locations in the study area. So this is all about ground response analysis. And as ma'am mentioned about micro tremor studies, and this is also one part of local studying local site effects. Here from this particular HYV method of micro tremor studies, we can find out the predominant frequency of the soil as well as the amplitude of the soil, predominant frequency and the corresponding amplitude of the soil. So why we have mentioned H by V method is, this H by V method is given by Nakamura. Okay, so why we have mentioned H by V is two horizontal components by sum of two horizontal components which are nullified by the vertical component. That is the ratio of two horizontal components to one vertical component of the ambient noise. As ma'am has said, we cannot fix the particular foundation, and there are some small micro vibrations which we cannot feel in the soil. The main motto of this particular Nakamura H by V method and microtremor studies is to study those particular ambient noise which we cannot see, and to find out the predominant frequency of the soil. So here also we have taken randomly 75 to 80 locations in the study area. And how we have chosen these locations is mostly we have already collected the geotechnical data from different public and private organizations in the city study area. So based upon the availability of the practical data, soil data, we have chosen this micro tremor study locations also. So this is the field setup in one of the test locations, that is at the park. And one more thing is when we are doing micro tremor studies, we have to choose large open grounds. And one more obstacle in this particular study is we cannot do this particular testing in daytime, because we cannot mix the sounds or noises from the random coming vehicles, or while people are stepping out or while people are walking, and whatever the random noises which we are having, we cannot combine those particular noises with the micro tremors. We only want to study the micro tremors. That is why we have to choose large open grounds where there cannot be any disturbance by the passing vehicle or passing person. And one more thing is, we cannot do it while the people are moving. That is, either we have to do this particular test before early morning or late in the nights, after everyone stopped moving, approximately. So that is the main problem of this particular testing. So here what we do is after setting up this particular micro tremor testing equipment, we'll be doing this, we'll be leveling up this particular equipment. As you can see here, the leveling screws on the three sides of this equipment. This is the main equipment which will observe the ambient noise, and this is the connection box between the equipment as well as our own laptop. You can see here a laptop may be missing. So to transfer the signal files, so this is the connection box. So after leveling it and doing the baseline corrections and all, we'll be leaving this particular equipment for 60 minutes in that location without any causing any movements. Even we should also not move around that particular equipment, so it will be absorbing the ambient tremors from our footsteps. So that is why we should also not move around this. So if we leave it for 60 minutes, each minute it will be giving a signal file. Yes, here you can see the signal file of micro tremor recording at a particular location. And this is the procedure of for the analysis of H by V ratio. This equipment is provided with View 2002 software, where you can analyze the 60 signal files in a batch to get the frequency and amplitude spectra. Yes, so these are the H by V amplitude and frequency spectra after the analysis. Like for each minute, if we are getting 60 signal files, we'll be excluding first 1 or 2 minutes because of the disturbances we get. So after excluding those first 1 or 2 files, after that all the 60 files or 58 files will be batch analyzed, and we'll be getting the frequency and amplitude spectra. So based upon the frequency and amplitude spectra, we have divided the study area into 3 different zones. Okay, so 3 different zones, that is type 1, type 2 and type 3, like where the fundamental frequency of the soil is greater than 4 Hz, and in the type 2 of soils it is 2 to 4 Hz, and in the type 3 of soils it is 2 Hz, less than 2 Hz. And one more thing is, all the signal files are cut to 10 Hz max, frequency of 10 Hz, because like when we are constructing, our interest is only to provide the maximum frequency of 10 Hz, because no structure will be having higher frequencies of more than 10 Hz. So that is why we have cut the signal files up to 10 Hz. And yes, as you can see here, it is from 0.5 to 9.5 only. So in this 10 Hz, what is the peak frequency and the corresponding amplitude can be picked from this particular H by V frequency and amplitude spectra. So that is the predominant frequency of the soil. Here in this case, it is, as you can see, it is 1.2 Hz. Oh, sorry, not 1.2 Hz. It is around 4.2 or something. And the corresponding amplitude is 1.2. So from this microtremor studies, we can pick the frequency and H by V amplitude values for each location. So here in all the 75 locations, we have to conduct testing, and from the testing we can get H by V frequency and amplitude values. So I have given for you few plots only for type 1, type 2 and type 3. That is frequency greater than 4 Hz, and frequency 2 to 4 Hz, and frequency that is less than 2 Hz. Here what this is the classification, and the observed values of what are the different types of soils we have. As we have already got the geotechnical data, like we have cross-checked the results. What is the type of the soil we have, and the SPTN values and shear wave velocity values. So this is the classification. Yes, based upon the H by V frequency value, I have prepared a hazard map, and this is the hazard map where we can pick the predominant frequency of the soil. And this is the amplitude map of the study area, we can pick the amplitude of the soil. And yes, so why we have to pick frequency values from this particular map? That is if the predominant frequency, fundamental frequency of the soil coincides with the fundamental frequency of your structure which you have constructed. If both the fundamental frequencies coincides, resonance effect will be occurring, and which will lead to huge damage during an earthquake. Okay, so that is the main motto why we have given peak frequency maps for this particular study area. So when we are doing earthquake resistant designing, or when we are going to decide the critical height of the structure, while doing earthquake resistant designing, we'll be having a situation where we have to decide the critical height of the structure. So based upon that, based upon the frequency of your structure, we can based upon the frequency, the predominant frequency of the soil, we can choose the critical height of the structure. Structure height can be changed, whereas this particular fundamental frequency of the soil cannot be changed, right? So depending upon the fundamental frequency of the structure, we can change the critical, we can decide the critical height of the structure. So here it is vulnerability index map. So vulnerability index kg is nothing but amplitude square by frequency for all the locations. So Nakamura has proposed this particular vulnerability index, where the vulnerability increases, the damage of the structures also increases that in that particular area. Okay. So, but depending from this particular study, we have not seen that much of vulnerability of the structures. So after that, we have proposed a frequency depth relation. Okay, actually we have chosen some 35 locations which where we already know the depth of the bedrock from the geotechnical bore log data which we have collected. Around 35 locations we have taken, and after linear fitting it linearly, we have got a frequency depth relation. So using this particular frequency depth relation, we can find out, if we know the frequency, we can find out the depth of the bedrock at other locations also. And here we have cross-checked the results, like how far this particular equation is feasible to use in order to find out the depth of the bedrock. And we have found out, from the literature and all, we have find out marginal error of 15% is acceptable. And mostly when we try to calculate this particular location of depth of bedrock for other locations also, uh, we have seen that the marginal error is less than 15%. So these are the few typical findings from the micro tremor testing. The frequency values are below 10 Hz, and the how we have divided T1, T2 and T3 sites. Okay, so these are the few how we have decided the T1 sites and T2 sites, that is the sites with rock and gravelly soils. As I have already said in the previous study, northern part of the city is having some rock outcrops. Here also, as you can see, the northern and central parts of the study are classified under T1 with the rock and gravelly soils with pebbles. So few rock outcrops are found out in northern parts of the study area, and similarly in southern and western parts, it is the frequency is between 2 to 4, where we found out clay and silty sands. Okay. So here less than 2 is found out in the soft marine clay sediments, where higher amplitude values are found, and these are classified into T3 sites. So the next one is liquefaction studies. So here, as we can see, from the results from the ground response analysis and from the micro tremor testing are a bit they are coinciding. As you can see from the statements, as well as I have mentioned in the ground response analysis also, they are coinciding. We have cross-checked the results between the numerical analysis to the experimental part. Ground response analysis is completely numerical part, which is done in the deep soil software. It is an open source software. And after that, in the micro tremor testing also, we got coinciding results, the results got matched. After that, it is liquefaction studies. Here what we have done is we have done liquefaction studies both in stress based approach as well as energy based approach. Most of us know liquefaction analysis can be done, liquefaction potential assessment can be done using stress based approach, which is proposed by Seed and Idris in the 1981 and 1971, and after that it was modified and improved by many researchers, and we have followed the procedure given by Idris and Baulanger, which is given in the year 2008. That is the most recent version of stress based approach after Seed and Idris. So this is the method followed is Idris and Baulanger method. Here, as we already know, the stress based approach is nothing but where we'll be finding out the cyclic stress ratio to the cyclic resistance ratio, CSR by CRR. So here in this study, as we already know, we can randomly pick a P ground acceleration of 0.1 g in this liquefaction analysis directly from the IS code. So instead of doing that, what we have done is we already have the site-specific ground response, site-specific peak ground acceleration values from ground response analysis, which is the first part. So we have picked ground PGA values from that study, ground response analysis, and we have done liquefaction assessment. So like the results will be like accurate. Instead of using the codal provision value 0.1 G for all the locations, we have taken like PGA values from the GRA for each location, that is ground response analysis for each location, and we have done liquefaction potential assessment. So these are the few plots which are showing effective stress SPTN values and shear wave velocity values. And this is the liquefaction hazard map using stress based approach. So here also we can find out the locations which are liquefiable and which are not. And the next one is energy based approach. This is a bit new when compared to the stress based methods, which we already know. Like stress based methods are the like conventional methods which are followed since long time, whereas energy based methods are which are recently formed and which are recently in use, and this method can be used to cross check SBM. Like it is not mandatory to cross check SBM, but we can validate the results actually. So this energy based method of liquefaction potential assessment is completely based on like the energy which was released from a seismic wave. Like when we have an earthquake, whatever the energy released, upward energy from the bedrock to the surface, energy released to the ratio of energy released to the energy dissipated, like how much energy of how much amount of energy is released to how much amount of energy is dissipated. If the more energy is dissipated, like less chances of liquefying the soil will be there. If very less amount of energy from the seismic wave is dissipated while traveling from the bedrock to the surface, then there are higher chances of liquefaction, and which obviously results to the damage of the structure. So that is the main concept in this energy based method. We'll be calculating the energy released from an earthquake depending upon the PGA values and all, and then we'll be estimating the energy dissipated, and then we'll be taking the energy ratio, which is energy released to the ratio to the energy dissipated. So these are the few plots which are showing energy ratios, and this is the one which is showing liquefaction hazard map. Here also the above 2, when the factor of safety is above 2, there are no chances of liquefaction. When it is from 1 to 2, the soil is likely to liquefy, like the chances are 50-50, and when it is below 1, it is completely, the soil is completely liquefiable. So depending upon these values, we can identify the sites which are liquefiable, and we can go for some mitigation measures and some ground improvement techniques in order to arrest that particular liquefaction in the soils, or we can do some changes in our designs too. So these are some typical results from both stress based approach and energy based approach. So now so finally the thing is like we have done seismic hazard assessment, that is probabilistic seismic hazard assessment, and then we have provided some preliminary microzonation maps. Microzonation maps in the sense whatever the peak ground acceleration maps and this predominant frequency maps, predominant frequency of the soil maps, and amplitude maps, vulnerability index, liquefaction, all these are the preliminary microzonation maps which can be used for general planning and disaster management as well. And these will be helpful in identifying the sites with higher ground accelerations. So coming to the application of all these dynamic site characteristics, whatever the dynamic predominant frequency, we have peak ground acceleration of the study area, as well as the site specific peak ground acceleration from ground response analysis, and amplitude values. These values are given as input, and we can construct a site specific response spectrum. I can show you here. Yes. This site-specific response spectra given by IS 1893 for the maximum credible earthquake as design-based earthquake, which are level 2 and level 3. These MCE and DBE are the curves which are uh, taken based upon the site-specific values. Here I have used Eurocode 7 for constructing response spectra for this particular site of Vishakhapatnam. That is for maximum credible earthquake level, level 3, and design based earthquake, that is level 2. Okay, so for level 2 earthquake and level 3 earthquake, we have constructed site specific response spectra. And if we give input this particular input of these particular site specific response spectra in USGS is a site where we can find a lot of earthquake ground motions and all. So it is a earthquake database actually. So if we input this particular site specific response spectra values, that is time period versus spectral acceleration values, we can get the earthquake strong ground motions that can be related, that can be used in our study. Like as Vishakhapatnam is in zone 2 and it is not having any strong ground motions that can be used for any analysis. Suppose if we are doing it for some Gujarat, we can directly take Bhuj earthquake ground motion for the dynamic analysis or static analysis, whatever it is. Static nonlinear or dynamic nonlinear, whatever it is, time history analysis or this pushover analysis. For all these analysis, we can, if we are doing a sort of problem in Gujarat, we can directly take Bhuj earthquake ground motion. But here in Vishakhapatnam, as there is no strong ground motion available for any sort of analysis, if I wanted to do some dynamic analysis of a structure in this particular study area, though I have dynamic site characteristics, I don't have any ground motions to give it as an input. So here what we have done is, we have constructed using Eurocode 7 and 8, we have constructed this site specific response spectra, which are different from the IS code. As you can see, IS code values are underestimating. As you can see from the spectra, IS code values are underestimating. So based upon this particular site specific response spectra, I have taken them as an input, and I have used USGS earthquake database, and I have found ground motions which can be connected to my site. Based upon this response spectra, I have found out the ground motions which can be used for my site, and we have done time history analysis as well as pushover analysis for the warp structure. So this is a warp structure which we have taken. As you can see, the diameter of the piles as well as the main beam and all. Yes, this is these are the specifications given by the port authorities, what is the size of the vessel that can be expected in at this particular wharf, what is the draft, what is the overall length of the vessel that is expected. Like these are the maximum values specifications, and we have done pushover analysis as well as time history analysis, which are not presented in this particular presentation. So I'm just telling the application of this part, all the dynamic site characteristics which we have found earlier can be applied to pick some strong ground motions which can be used for the analysis. So with this, maybe I can stop my presentation and
Okay, madam. Next, Nishita.
Ma'am?
yes.
Ma'am, there are certain questions.
Yes, ma'am.
Ma'am, what is the reason behind less energy dissipation area have more liquefaction? Please explain.
Obviously, whenever we have seismic energy, which is traveling from the bedrock to the surface, if more of energy is dissipated by the soil, when it comes to the surface, we'll be having very lesser amount of energy, and obviously liquefaction will be lesser, right? Seismic energy amount which is released at the bedrock, if it is same, like while it is traveling from the bedrock to the surface, what happens is, depending upon the soil site conditions, either the energy is dissipated or the energy is increased, right? If it is having a soft soil bed, the energy will be amplified, the seismic waves will be amplified. That means more energy will be traveling to the surface, which results in which results in higher chances of liquefaction. But when more energy is dissipated, only a little amount will be traveling to the surface, which causes a lesser, which will lessen the chances of having liquefaction in that particular area, depending upon the local, the soil strata which are present between the bedrock and the surface. If the soil strata is soft and it is having a tendency to amplify the seismic waves and increase the seismic energy, it will result in higher liquefaction chances. When the soil strata is stiff, something like rock or a stiff gravel or something like that, then it will be dissipating the energy. Obviously liquefaction chances will be lessened.
Right. Thank you, ma'am. Ma'am, one more question I have. Ma'am,
Yes.
in the first part of the presentation, you said that there were some predictions regarding the specific site locations. So, ma'am, for how long duration are those predictions valid?
How long, in the sense, when it comes to zone 2, you are asking about seismic hazard assessment, right? Yes. When it comes to zone 2 or zone 3, which are having very less number of earthquakes, and in zone 2, as I have seen, there are no huge earthquakes of 6 or 7 recently. So when there is increased number of earthquakes, when it comes to North India or Northeast India, mostly, even though if you have more number of earthquakes, whatever the results you have will not change mostly, so you can use it for a long period of time. So see, when we come to SK Nath and who have done it for Sikkim and northeastern states, they have done it long back for whatever the earthquake data they have. And now recently, while people are doing research in this earthquake research in this times, though we take the data from the recent times, so if he has done it from some 1800s to 1900s and got some results, and I am doing it from 2017 to back, 1917 or something, so for the past 100 years, though we do in a different time periods, the results will be coinciding. We can validate the results.
So there is not much variation in the results
Much
as such.
variation is not expected when you don't have increased seismicity. So if there are lots, when we see geologists telling that when we have increased seismicity, then we can expect a different, a bit difference in the results.
Yeah, got that, ma'am. Ma'am, one more thing. The micro tremors study, how is it useful, ma'am?
See, when we get the predominant frequency of the soil, generally we don't take predominant frequency of the soil in designing part, right? So when we have this predominant frequency of the soil, and if you are going to construct a structure on that particular soil, what happens is you have to decide the critical height of the structure. If the natural frequency of your structure will also be having a natural frequency, right? So if your natural frequency of the structure coincides with the natural frequency of the soil, resonance occurs, which results in higher chances of damage, huge damage during an earthquake. So it is obviously better to design your structure, or decide the critical height of your structure based upon this frequency value. We should see that both are not coinciding.
So, ma'am, the frequency of the structure should be more or less?
More or less is depending upon like a single change in the structure will be changing the frequency of the structure, right? So it depends upon your requirement whether you are going for a high rise structure or a low one. So it depending upon the requirement of the structure will go. It just should not coincide. That's it.
Thank you so much, ma'am. One more question by Satyaprakash, sir.
Yes.
He has asked which method should we follow while preparing hazard maps while we have geotechnical data in a discrete manner over an area, interpolation or any other method?
Interpolation. Okay. So hazard maps, discrete manner. When we have discrete manner in the sense like when we don't have the points in a like arranged manner, right? So here I have used a triangulation method. In GIS, we'll be finding triangulation method where we can go for preparing hazard maps.
So I hope that question is answered, sir. If you have any other query, you can also unmute yourself and discuss it with ma'am. If any of the participants want to have any questions raised or they want to have a discussion with ma'am, you're most welcome to unmute yourself, or you can even type in the chat box. Thank you, ma'am. That was from Satyaprakash, sir.
Thank you, ma'am.
Yeah, ma'am, Vaishali ma'am has also responded with a thank you.
Or we
So,
have please explain what other factors test we can consider. How to calculate the critical height by. See, H by V value is not used to calculate the critical height. It is just used to decide. So your critical height will be affecting the frequency, predominant frequency of your structure. Fundamental frequency of your structure will be calculated using your critical height, H value, right? So it is just whatever the predominant H by V frequency value of the soil is entirely different, and predominant frequency of your structure is entirely different. It is nowhere related to the calculation of critical height. So when you calculate your critical height, when you calculate your frequency, yeah, critical height of the structure is used, H value is used, right? So it is just used to decide. You can either increase or decrease the height of the structure in order to avoid that coincidence of natural frequencies of both soil and the structure. That is, it is just to decide, not to calculate. I guess that is justified.
thank you so much, ma'am. Ma'am, if anywhere, if there is already constructed building, can this study be useful over there?
Yes, micro tremor maybe like we cannot put it on the soil or like we can find out what we say the fundamental frequency of the structure by doing the micro tremor study on the structure itself, but there is no way related to the constructed structures.
So this study is supposed to be done before the construction is to be taken place.
Yes.
Thank you so much, ma'am. So any of the participants, if they have any other further questions, we welcome you to have an interaction. So, ma'am, I think all the questions in the chat box have been answered by now.
Yes.
And thank you so much, ma'am, for this
Thank you very
wonderful
much, ma'am.
explanation.
Thank you,
For the
sir.
wonderful
These values
explanation of
are
work.
like the fundamental values that can be used for earthquake resistant designing. Dynamic site characteristics. Most of the time, even till my PG also, I have not used any site specific values. We'll be randomly picking some values from the IS code, whether it is related to geotechnical engineering or whether it is related to structural engineering. We'll be randomly picking the values from IS code and we'll be using them same in the earthquake resistant designing. But here, the main problem is, as I have shown, there is a lot of like a bit of difference from the IS code values that are provided and the values that are practically taken from the experiments. So here, if it is zone the of difference, we can expect a lot of difference in the zone 4 and zone 5. It is not mandatory, but at least there is a chance of having difference from the IS code values, because IS code has provided the values in a larger perspective, like it is macro zoned, whereas here the site specific studies are to the pinpoint, like to that particular location. So there will be a difference, and which will be increasing the efficiency of the design, as well as which will be increasing the safety, which ensures the safety of the structures. That's it.
Right, ma'am. So thank you so much, ma'am, that you have brought to our notice that site-specific studies are really important, and that IS codes are just a broader view of the criteria that are supposed to be taken. So that was a wonderful presentation by Priyadarshini ma'am. We thank ma'am for taking out time from a busy schedule and then enlightening us over the experimental work that you've carried out, sharing us your experiences, and definitely inspiring us to work in the direction of this seismic hazard risk assessment.
Yes,
Thank you
I
so much, ma'am.
especially thank Amit Sharma sir as well as Nilima Satyam ma'am for giving me this opportunity to share whatever I have done to the people. Like, see, many of us don't know what are the open source codes that are available for this particular earthquake geotechnical engineering. So even I came to know after joining with Nilima Satyam ma'am only. So it will be helpful for students also to use those open source codes and do some sort of dynamic part in this in their studies.
Ma'am, it will be
Yes,
nice if you can share us the details of those codes, ma'am.
Like, there are many open source softwares as well as open source codes that are available. Even Neelima ma'am has also done few using her from her students. Like, Liquefaction tool is available with Neelima ma'am, where you can input the just the values of whatever the density and depth of the water table, whatever the size of the unit, and you can diagnose whether and we are also having other softwares like deep soil, and QGIS can be used for preparing hazard maps when we don't have access to ArcGIS. Okay, so and there are a lot more. Maybe I can share you with Amit sir later. But there are a lot
okay.
more open sources in earthquake geotechnical engineering. I'm sure you can find it if you browse it somewhere. So they'll be helpful for the initial or BTech or PG people can do something different with these codes or software tools.
Yeah, thank you very much, madam, and I hope that our participants and I believe that our faculties will contact you and Nilima Satyam, madam, for their further knowledge, and I hope that will make a bridge of research
Yes,
for
sir.
all of us actually.
Yes, sir, sure. I am willing to help anyone with these in this part of earthquake geotechnics. So I'm sure I can help it. If anyone is going to contact, you can just go with Nilima ma'am, and she'll contact with
Sure,
me.
sure, sure.
Ma'am, we need your guidance in future as well.
Sure. In
Uh,
this earthquake geotechnical engineering, I'm sure I can help whatever I can do.
Thank you so much, ma'am.
Thank you so
Thank
much
you,
for
ma'am.
giving the opportunity, sir. Thank you.
Thank you very much,
Thank
ma'am.
you, ma'am.
Thank you, ma'am.
Thank you, sir.
So this was the session 2 of the faculty development program, and we hope to see you after a lunch break at around 2 p.m. for the next session that is supposed to be scheduled. And that's all for now for the participants. We'll see you after a lunch break.